So this is question 3. Um, Same question we did before. If you haven't watched the previous video, I recommend you do that, and then you come here and then you try doing this yourself, and then you compare the solution, or you can just first watch the video. I don't care. Plant has transfer function P of S equals 7 over 16 s squared. Blah, 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 blah. Design a feedback controller such that the closed loop system has a pair of poles at S equals -1 plus minus j root 3 over 4. What is the steady state error in response to units that propose a modification to your controller? Okay, so we're gonna ignore this part for now. We're gonna do this part later. The first part, plant has transfer function. So if you set P of S equals 7 over 16 over S squared plus S plus 7 over 16. This is my plant system. And just because I always like to have it, you have plus and minus, and in this course, we're not responsible for designing a feedback gain or a feedback system. We just have a y of s that comes in directly. And here's my plant, which is given to me, and here's my controller, which I'm going to design with some gain. Cool. The closed loop system, I'm told that the closed loop system, that the overall row here, is going to have a pair of poles at s equals -1 plus minus j root 3 over 4. So what I desire, SD, is equal to -1 plus minus j root 3 over 4. In short, if I was to draw this on a plot, we would have it at -1 j root 3 over 4, and root 3 over 4 really is like 0.4. Okay, so it's like somewhere over here. Okay, let's like expand the scale a bit. Sorry. Here's -1. Here's 1. Here's -1. Here's the imaginary. Here's the real axis and the imaginary axis, and so this would be around 0.4. So this is so it would be somewhere up here. So it would be it'd be somewhere over here. This is my desired pole. At root 3 over 4. Now, what is the steady state error in response to a unit step? What is the steady state error in response to a unit step input? Okay. Well, none of this matters right now. We're still in the first part. We're port A, and this is port B, and this is port C. Port A is designed the feedback controller so that the closed loop system has a pair. We're here. We're stuck on this part. Right. This is like a loaded ass question. This is a huge question, actually. So we're on the first part right now. So the first part in and of itself is a question, right? That's like I'd say this is like 15 points at least. Where the designing of the controller, we know that SD is -1 plus minus 0 3 over 4. What this means is that the system, the overall system, needs to have the poles at -1 plus minus 0 3 over 4, right? Okay, cool. And what do? First step is accepting the rule that the sum of the angles of the system is equal to the sum of the angles contributed to by the controller plus the sum of the angles contributed to by the plant, and this must equal to -180 degrees. Where, and this is where I went wrong in the previous video, the sum of the angles of the controller, C of S, is equal to, anything in the world is S minus Z over S minus P, zeros and poles. So because it's always in the form of Z and P, regardless of where these Z's and P's are, then because of this, it's always the sum of the zeros minus the sum of the angles contributed to by the poles. Okay. So in this case, I don't know what my controller even is. I need to design it. So I don't even know, this is a rule, right? I don't even know what the C of S is. I don't know what the angle is. But I know what at -180 is -180, and I know the angles of P of S. I know what P of S is. I know that P of S is equal to 7 over 16, 1 over s squared plus s plus 7 over 16. And the angle that P of s contributes at this point, to this point, for this system, for the desired pair of poles, is going to be the angle of PSD, right? When S equals SD. And so PSD is equal to 7 over 16, 1 over s squared plus s plus 7 over 16, where S equals SD, where SD is equal to, and we can choose either one, minus, we can choose plus or we can choose minus J root 3 over 4. I just go with the plus because like that's what everyone does. So, and then you just plug this into your calculator in phasor format and you can find the answer. And we'll get that the answer here is 7 over 16 all over x squared plus, oh, you have to put your calculator, yeah. So 7 over 16 all over x squared plus x plus 7 over 16. And your x must equal to minus 1 plus j root 3 over 4. Store that in x. And you'll get 7 over 8 phasor 6. I know I'm right because this is a nice angle and there's no decimals. And if you wanted to do a sanity check, I mean, you could. It's just useless, but like you would say that the phase of PSD is equal to the phase of the numerator minus the phase of the denominator. The numerator is just a real number, 7 over 16, so its phase is 0. So it's just going to be minus the phase of the denominator. The phase of the denominator, well, SD squared is equal to 1 plus j squared 3 over 4, like j root 3 over 4 all squared minus 1 squared plus 2ab, so 2 minus 1 j root 3 over 4. And that's going to be 1 plus minus 1 3 over 4 squared 16 minus 2 j root 3 over 4, so minus j root 3 over 2. And this is 16 over 16 minus 3 over 16 minus root 3 over 2j. And 16 minus 3 is 13, so 13 over 16 minus root 3 over 2j. And that's SD squared, and my full formula is s squared plus s plus 7 over 16, right? So it's going to be SD squared plus SD. That's insane. Okay, let's not copy paste anything anymore. Minus 1 plus j root 3 over 4. Oh, plus 7 over 16. And this is minus 16 over 16. And in that sense, we get 13 minus 16, that's minus 3. Plus 7, that's 4. So 4 over 16. And j root 3 over 4. And this is 2 root 3 over 4. So that's going to be minus j root 3 over 4. And the phase of this guy, and the phase of this guy is 4 over 16, and he's at minus j root 3 over 4. So and this theta is equal to what? So tan theta, or I can say that tan of x is equal to opposite, which is minus root 3 over 4. All over the adjacent, which is 4 over 16. Which would be, the calculator refuses to solve it for some reason, but opposite over adjacent 4/16. So divided by 4/16 is times 16/4. So it's just tan theta equals √3. So arctan of √3 is 60. And as you can see, this is negative. So the angle of the denominator is minus 60. And so that means that the angle of this guy is minus 60. And the phase of this guy is 0. And 0 minus minus 60 is 60. And so I can see that my calculator was actually right. But again, as usual, don't do this. Just because it's not required. Anyways. So yeah, the angle of PSD is going to be 60. And I know as a rule of thumb that C of S, or this guy, is going to equal to minus 180 minus the angle contributed to by P of S. In this case, that's 60. So the angle by C of S should be minus 180 minus 60, which is minus 240, and minus 240, 918 times, I guess it'd be somewhere over here, is nothing but 360 minus 240, which is equal to, I forgot math, 120. Right, so saying that CS has an angle of 240 is the same as saying that CS has an angle of 120 degrees, right? Yes, cool. So I need a compensator such that the angle of the compensator is going to form 120 degrees. Fair, cool. My understanding, which it could be flawed because I went to no lectures, says that a lead compensator is like this, and a lag compensator is like this. And the pole leads the zero in a lead compensator, and a lag means that the pole lags behind the zero and the lag compensator. And the desired pole is somewhere over here, and this will be the angle formed by the entity on the right, and this will be the angle formed by the entity on the left, right? So this is just theta of the zero, and this is the theta of the pole. And here's the theta of the pole minus the theta of the zero, where this is always the difference between the entity on the right and the entity on the left. I mean, this is theta z, so you can just think about it like this, this, this. And so this angle is theta z, and alternate interior angles. This angle is theta of the pole, and so this is the theta of the zero minus the theta of the pole. And in this case, it's because we flipped the names, it doesn't change the geometry. It just means that we now call this a pole, and we now call this a zero. And so this is theta of the pole minus the theta of the zero. In all cases, the angle of the CS is going to equal to the angle of the poles. The angle of the zeros minus the angle of the poles. The reason being, CS will always be, no matter what you call, like whatever you want to call it, it's a thing on the top is a zero and the thing on the bottom is a pole. And the angle of a CS is always equal to the angle of the top minus the bottom, so the zeros minus the poles, right? And in this case, I want the zeros minus poles to be a positive value. And because I want it to be a positive value, it means that I want it to be a I want it to be a positive value. Like, it's not that deep. I want it to be a positive value, which means that I want it to mean that the angle of the zero has to be larger than the angle of the pole. Which, just by looking at the graph, you can tell that if I want the angle of the zeros to be greater than the poles, I must use this guy, right? Because otherwise, the pole is larger than the angle of the zero, and I'm going to get a negative number when I do 0 minus p, right? So this is small minus big, and this is big minus small, and 120 requires a big minus small. So I use lead compensator. Cool. So now I know that my lead compensator has to be of the form 120 degrees. Let's just call this SD, where I know that SD given to me has -1, and I know that SD's height is √3/4j, and this is because SD is equal to -1 plus -j, or 3/4. And I know that the angle difference, theta z minus theta p, in the lead compensators, I know it's going to be a lead compensator, so I know I'm going to have a bro here and a bro here, and the guy on the right is a 0, the guy on the left is a pole. This is a pole, this is a 0, because I'm using a lead compensator for all the reasons described earlier. And I know that the theta z, theta p, theta z minus theta p equals to be 120 degrees. And so in this case, I can't use the right angle trick. I can't just say like, oh, just pick the right entity to be on the same bro as this guy and make it a 90-degree angle, because it's 120 degrees. So I can't have a right degree angle anymore because I need acute angles for that. So instead, I'm just going to say 180 minus 120 equals 60, and then the easiest geometry gives me that this is going to be 30 degrees away and this is going to be 30 degrees away. That's just the easiest geometry I have. And if I do it this way, knowing that this is at -1, then I know that, and knowing that this height is √3/4, then I know that tan of 30 degrees is equal to the opposite, √3/4, divided by the adjacent, which is x, such that x equals √3/4 divided by tan of 30, where tan of 30, I'm pretty sure, is like √3 or something. Yeah, √3/3. Oh, it's 1/3. Tan of 30 is 1/√3. So it's equal to √3/4 divided by 1/√3, which means I'm just saying divided by √3/3, which means I'm saying multiply by 3/√3, which means it's equal to 3/4, right? And you can see that's satisfied. Like √3/4 times 4/3 is √3/3, and that's tan of 30, and that makes sense. So this distance over here is going to be 3/4, and by symmetry, since this angle is the same, 30 degrees, and this angle is the same, it's 90, and this is the same, right? Opposite is the same, then this is also going to be the same. It's also going to be 3/4, which means that the pole is 3/4 units left of -1, -1 being the center equidistant point at which SD exists, and it's 3/4 units right of -1 for the 0. So the pole is -1 minus 3/4, and the 0 is happening at -1 plus 3/4, which means it's happening at -1/4, and it's happening at -7/4. So since I've used a lead, it doesn't, no, actually, it literally does not matter, because my compensator is always of the form s minus z over s minus p. So it means that it's going to be the form of s plus 1/4 to get a 0 at -1/4, and s plus 7/4 to get a pole at -7/4 is my compensator. This is part A of the, this is part I of part A of the question, right? Part I is, or like the second part is saying what is the gain, because it's not CS. If you look at original graph, it's actually K CS, correct? So what's K? So then you have to use the other rule, which says that your compensator shall not change the gain of the system at SD, meaning that your compensator's gain multiplied by the gain or the magnitude incurred by the system at the desired pole is going to be 1. There's going to be no change to the gain at all, which means K is equal to 1 over PSD CSD, where PS is equal to 7 over 16 over S squared plus S plus 7 over 16. Okay, please take this and put it. Okay, and can you please paste it without embarrassing me? Yes, okay, thank you. And CS is at S plus 1 over 4 all over S plus 7 over 4. So this is my PSD and CSD, or no, rather, this is my PS and CS. And so just literally take this and plug it into your calculator at S equals SD, which happens at -1 plus minus J root 3 over 4. And so just put your calculator in complex format and you say that you set -1 plus J root 3 over 4. You store this in X. So -1 plus J root 3 over 4. Store this in X. And then you say 7 over 16 all over x squared plus x plus 7 over 16 multiplied by x plus 1 over 4 over x plus 7 over 4, and you get, and I know I'm right because the numbers are easy. The numbers are very nice. So I get that PSD CSD is equal to 7 over 8 180 degree, which means that PSD CSD that is equal to 7 over 8. In which case, K should be the inverse of that, which means K is equal to 8 over 7. Yuck. Really? Yeah, K should be 8 over 7. Okay, I'm no longer certain that I'm right. Wait, I mean, yeah, no. K can be greater than 1. Yeah, K is it's just a gain. It's just a gain. Yeah, of course. Okay. Yeah, of course I'm right. Yeah, okay. And I guess if you wanted to like show your work, you could like do 7 over 16 S plus like 7 over 64 over like S cubed plus S squared plus 7 over 16 S plus 7 over 4 S squared plus 7 over 4 S plus 49 over 64, and you could like collect the terms such that this is 4 and 7 is 11, so you get like 11 over 4 S squared, and 7 over 16 plus 49 over 16 is 56 over 16. S plus 49 over 64. I guess you could like do this. And then you can just plug it in your calculator again. Like this is pointless. Or unless you unless you sub in this as the, and then you multiply by the complex conjugates, and then you get real and imaginary, and then you do a squared plus b squared all square root. But I'm literally not going to do that because I don't care. I'm not doing that. Okay, so K is equal to 8 over 7. And so finally, my answer is my C of S, my compensator, is going to be 8 over 7 as my gain times S plus 1 over 4 over S plus 7 over 4. That's my CS. Oh, I should not have erased that. Okay, shit. Okay, go back, because I'm going to need it for the next part. Okay, apparently you will need to expand. Okay, solid. Yeah. So we said that CS, PS multiplied together is going to be 7 over 16S plus 7 over 64 all over s cubed plus 11 over 4 s squared plus 56 over 16 s plus 49 over 64. And we said that my answer to part 3 is just going to be that C of s equals k 8 over 7 times the value of CS that we got here, which is s plus 1 over 4 over s plus 7 over 4. Which means that if I begin part B with the question of what is the steady state error response to a unit step input? What is the steady state error response to a unit step input? Then I can say that the steady state error in response to a unit step input, part B, is, bro, enough, bro. KCS is just going to be 8 over 7 times this guy. So this is my KCSPS. This is the guy. You're asking me what is the steady state error in response to a unit step input? What is the steady state error in response to a unit step input? So the steady state error in response to unit step input is just going to be limit as s approaches 0 of y of s y of s. This is by the finite value theorem, right? Limit as s approaches 0 of s y of s. What is the steady state error? What is E of s? Oh, you're not giving me. You're asking me what is ESS. What is ESS? Bro. In response to unit step input. So in response to a unit step input, I suppose the limit as s approaches 0 should be something. It will be something. And the unit step should have a value of 1. And so I guess I can just find the difference. And that's your steady state error. I'm not certain actually. So I'm going to end the video in part for this part, just for this guy. And I'll struggle a bit for the next one and see what I can do.